Alright, welcome back everybody. In this video we're going to talk about material related to section 8.4 of AP Calculus, finding the area between curves expressed as functions of x. And this lesson is going to go over exactly what it sounds like. We're going to talk about how we find the area between two curves when they are expressed as functions of x. Okay. A little bit of a definition about how that works. It's actually pretty straightforward. We had some complexity when we talked about, area between a curve and the axis, where we had to pay attention to whether the curve was above the axis or below the axis. We don't really have anything like that to worry about when we're finding the area between two curves. It always kind of follows this same kind of idea. So if I have two functions, f1 and f2, that are continuous, where f sub 1 is the bigger of the two throughout the interval that we're talking about, then the area of the region between the curves from A to B, we just take the upper curve minus the lower curve. And so, in essence, that's all we're really doing here. In order to find the area between two curves on a given interval, we take the integral from one end of the interval to the other of the upper curve minus the lower curve with respect to x. Okay? So what we're really looking at here, and you see this here, is that we've got rectangles that we're using, like we did back when we talked about Riemann sums with areas under curves in general. Only now, instead of the height of the rectangle being from the axis up to the curve, now the height of the rectangle falls in between these two curves. There's the height of the rectangle, and then the width of the rectangle is dx, and that gives us our whole setup as far as this goes. All right, what else do we need to be concerned with? Well, we need to make sure everything in our integral is in terms of the same variable, that the limits of integration are x coordinates, and that the functions are functions in terms of x, and that we integrate in terms of x. Other than that, pretty straightforward. Here's the process that I've been teaching for years to handle this particular concept. Step 1, graph the curves that form the boundaries of the region. We're going to either do that by hand, or sometimes we'll do that with a graphing calculator to determine which curve is the upper curve and which curve is the lower curve on the given interval. Once we've graphed the curves, we can find the limits of integration. Those will sometimes be given to us. We might say find the area between these two curves from x equals 2 to x equals 4. Well, that really gives us our limits of integration. Or sometimes the limits of integration are determined by the intersection points of the two curves. Then we set up our integral from a to b of upper curve minus lower curve with respect to x. And then we integrate the function to determine the area of the region. And again, how we integrate the function is going to be dependent on, is this a calculator section, a non-calculator section? What do my directions tell me to do? In general, if you're told to do it by hand, do it by hand. If you're told to do it using the calculator, or if you're doing it on a calculator section of the exam, by all means, do it with your calculator. And then other than that, you can kind of decide and pick and choose as you see fit when you encounter these problems. All right, let's go ahead and we'll start looking at some examples here. First example, we're going to find the area between the curves y equals negative x squared plus 4 and y equals sine of x from a equals negative 1 to b equals 1. So if I imagine these two, if I sketch these two curves, y equals negative x squared plus 4, downward opening parabola, and y equals sine of x. Well, I don't know exactly where. I know it crosses through there. I don't know exactly where it hits this sine curve, hits the parabola, so I'm just kind of guessing here. If I went and looked at these two curves, just to double check, y equals negative x squared plus 4, and y equals the sine of x, and I think I'm pretty close to spot on. There's our parabola. There's our sine curve. I didn't do too bad with the sketch of this graph. So what we're looking at here is we're finding the area between these two curves from a equals 1 to b equals 1. And again, if you look at the graph on here, you see that a equals -1 and b equals 1 are, right about here. Here's where x is -1, and right about here, here's where x is 1. And so we're finding the area of this region right here. Okay, so now to set this up, I'm going to take the integral from the left end of the region to the right end. Okay, the left end happens where x is equal to -1. And the right end happens over here where x is equal to 1, so that's going to be my upper limit. There's my limits of integration. Excuse me. And now I'm going to take upper curve minus lower curve. The parabola is the upper curve. And there's my setup to find the area. And at this point, I could integrate this by hand and substitute values in, but I'm just going to go ahead and use the numerical integral feature on my calculator, save us a little bit of time as we're calculating here. At this point in the course, you should be fairly comfortable integrating things like this by hand and getting an exact answer. For us, in this case, I know that since I'm putting, 1 and -1 into sine, I'm going to have, sine of a number as part of my answer if I do the, do the exact value by hand. So I'm just going to go ahead and get myself a decimal. Historically, the vast majority of free response questions on the AP exam on this topic are on the calculator section. So you tend to approach these problems this way more than by hand, but you should be capable of doing them by hand, just in case they show up on your non-calculator section. All right, I guess out of due diligence, I'll do this one by hand too, just so you can see what happens here. Since we kind of got a pretty nice answer, 7.3 repeating. If I do the antiderivative of all this, this is -x cubed over 3 plus 4x plus cosine of x, evaluated from -1 to 1. And then I do my substitutions, and I've got -1/3 plus 4 plus cosine of 1 minus 1/3 minus 4 plus cosine of -1. If you know your unit circle well, you know that cosine of 1 and cosine of -1 are the same value, and therefore this becomes, what is that, 11/3 minus -11/3, which gives us 22 over 3 as our exact answer, which is, of course, 7.3 repeating. All right, so for those of you who wanted to see one by hand, there's one by hand. All right, let's go ahead and we'll look at example 2. I'm going to go ahead and graph the curves, y equals x squared, and y equals -1/2 x plus 4. Now in this one, there are no boundaries, no side boundaries given, and so the limits of integration, the side boundaries of the region, are just going to be the intersection points of these curves. So I'm going to go ahead and graph the curves. There's my parabola. There's my line. Okay, so we've got parabola. We've got line. And so this is my region here. I need 2 intersection points here in order to find the value for the area. I need the coordinates of both of those points. I could, of course, find those by hand by setting the 2 equations equal to one another, but again, I'm going to proceed with this based off of the assumption that for the most part, when you're doing problems like this one, you are going to be doing them with a calculator in your hand when it comes to your AP exam. So I'm going to go ahead and find those intersection points. Let's see, find my intersection points. Oops. Got to pay attention to what I'm doing. I just tried to give it the same left bound and right bound. That was a bad decision. Here we go. All right, so the x-coordinate is the important coordinate here. I mentioned at the beginning of this video that, we're taking the integral. Everything associated with this integral to find the area should be in terms of x. That means that the intersection point where we want the x-coordinate. A lot of times when I'm doing problems like this, if I've got a graph and I'm doing a bunch of things with that graph, I'll just find all the intersection points and write them down on my graph and go from there. In this case, I'm just going to bring that intersection point over. Remember also, we want our final answer to be accurate to 3 decimal places. Sometimes if we cut our limits of integration short as far as rounding goes, it can impact the accuracy of our answer to 3 decimal places. So I'm going to actually use all the digits that my calculator gives me. So negative 2.265, 564 is what I'm going to use as my lower limit of integration. And as my upper limit of integration, I'm going to go ahead and find that intersection point. Boom, boom, boom. We get 1.765, 5644. 1.765, 5644. All right, so now we have everything set up, and we can go ahead and use our calculator to find the area. Especially when I have decimal limits of integration like this, it screams at me, use your calculator to find this, because Lord knows I don't want to substitute these in by hand. The only way I'm calculating these by hand is, really with a calculator in my hand, so it doesn't make sense. If I have a calculator in my hand already, let's use the numerical integral function. And so I go ahead and type my integral in. And I get 10.918. 10.917 is also acceptable as an answer. All right, and I think that's where we're going to leave off with this video. We'll come back and do the last couple of examples in our second video on section 8.4. All right, everybody, have a good rest of your day, and we'll see you next time. Enjoy yourself. Bye-bye.